Hello, chemist. Jolly again. Let's finish up this basic equilibrium chapter. So the last thing we need to talk about is one of the funnest, is Le Chatelier's. Okay, so the factors affecting equilibrium. So you've seen how to come up with the equilibrium expression. You've seen what the K value means. Now let's see, what can happen to it. If I'm really in equilibrium, that means if I upset it, it should shift to fix whatever I upset. So Le Chatelier's principle says, if an outside influence upsets an equilibrium, that system will undergo a change in the direction that counteracts that disturbing influence or force. And if possible, it will return it back to a state of equilibrium. Well, what could you possibly do to upset it? Well, there's many things. You could add or remove, okay, either a reactant or a product. If you are dealing with gases, you could change the volume or pressure, or you could change the temperature. All right. So I have a little blurb right here. And this is my Le Chatelier picture, so you can always go back and look at it. So I have A plus 2B is in equilibrium with 3C, D, and heat. So this is an exothermic reaction because heat is a product. Well, here is how you to read my table. The box that's bolded right here is what I did, okay? So to upset this equilibrium, I increased my A, okay? So I put too much A. There's the original, I'm at equilibrium, and now I just put too much. So my equation has too much A. How is it going to fix that? Well, it needs to use some of that A up by shifting to the right. And as a consequence, okay, as a consequence, I'm going to have to use up some of my D that I had, but I'm also going to gain some of my products. And don't forget, heat is just a product. All right, let's try another one. All right, this time, let's take away D. Okay, so we're going to decrease it. Okay, so whole new problem. I'm going to remove some A. I'm going to take it out. Not easily done, but I'm going to take it out. Oh, I don't have enough A, so my system needs to make more A, and the way to make more A is to shift to the left. As a consequence, I already had some B and I have a little bit more, so that's going to increase, but I had to use some of my C, some of my D, and I had to use some heat in order to do that. All right, so let's take a look at B. If I increase B, change colors. If I increase B, okay, I'm putting some in. Come on, eraser. Good enough, I guess. All right, so I'm going to add some B in. Now there's too much. Equilibrium is going to have to try and use some up by shifting to the right. And as a consequence, what's going to happen? I'm going to have to use up some of my A. Oh, I'm going to cough. I'm going to pause you for a second. All right, let's try this again. All right, so I'm going to shift to the right. And as a consequence, I'm going to lose some of my A, but I'm going to gain my products. Now, it's going to do the exact same idea if I'm playing with the product side. So this time, I'm going to use one of the products up. Let's use purple. This time, let's play with C. All right. Sorry, I had to pause you again. Let's see if I can make it through without coughing my head off here. Okay, so I'm going to increase C. So I have too much C now. Let's see if I can get these to erase. Oh, come on. All right, so I am putting extra C in. I have too much C, and so the reaction needs to get rid of it or use it up. So it's going to shift to the left. And as a consequence of that, it's going to have to use up some of the products, but I'm going to make more of the reactants. All right, let's do this heat. One more color. Ooh, pink. All right, let's increase the heat. So, put it on the hot plate, do something with it, but I'm going to increase the heat. It's just a product. Okay, if you increase the heat, there's too much heat, and in order to get rid of it, it needs to shift to the left. As a consequence, you're going to have to use up some of its partners, and you're going to make some more of the reactants. Vice versa, if you were to take it away. So if you decrease, this would be cooling it, and that would be taking it out of the solution. And so equilibrium would shift to the right. All right, so that is the nuts and bolts of Le Chatelier's principle. Well, what happens if there's gases in there? Well, then you just have to take into account, pressure and volume, because that can change. Go back to black here. All right, so in this case, A plus 2B is going to 3C plus D. All of them are gases. So everything that we just did is valid, but we're also going to add changes if I change the pressure and the volume. All right, so this side has 3 moles of gas, and this side has 4 moles of gas. So if I increase the pressure, okay, if I increase the pressure, that means the volume is going to decrease. All right, because remember, they're linked for the gases. So if I increase the pressure, I'm going to decrease the volume, so there's less room. Well, which side of the equation takes up less room? That would be this side. So in this case, it shifts left. All right, well, what if I decreased the volume? If you decrease the volume, that in essence is the pressure. If you decrease the pressure, you're increasing the volume, so you have more room. And which side has more moles to fill it up? This time you would shift to the right. And that's how you would play with pressures and volumes. But it only affects the gases. So what if they're not all gases? That's okay. You would just look at the overall amount of gases on each side. Oh, look here. Catalysts do not change equilibrium. They get to equilibrium faster. But catalysts do not change equilibrium. So what would happen if I added a catalyst to this? Which way would it shift? Neither. Okay. It would get to equilibrium faster, but then the catalyst doesn't do anything to equilibrium. So the last one I want to play with is temperature. Now, we did play with temperature down here as an XO, but if you increase temperature, it favors endothermic reactions. Well, duh, because it's one of the reactants. If you decrease the temperature, it favors exothermic. Well, yeah, because you're playing with it as a product or as a reactant. But here is the big, 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 big factor. It's the only value that can actually change the value of K. And this should look a little bit familiar. This is called the Van Hoff equation, but you can take 2 conditions, and these are the equilibrium constants. And you can actually figure out the enthalpy if you have the 2 temperatures. So again, usually we, graph things to get more data, but if you only have 2 data points, you can see how the temperature would affect the K value. All right, just looking here. All right. Gonna go to the whiteboard one more time. Ooh, scary. Okay, what do we know about basic equilibrium? Number one, two opposing forces at the same rate. So I'm going to say two reactions that are opposing at the same rate. That doesn't mean they're equal. That doesn't mean they're equal. Two, you have to write an equilibrium equation, which means you have to put equilibrium arrows now instead, and then you can show which side is favored if you want to do different lengths. Okay, but you have to use equilibrium equations. You can write equilibrium expressions. So that's the big K. Okay, that's the constant, is equal to the products multiplied together to their coefficients all over the reactants to their coefficients. And you may plug in molarities or pressure at equilibrium. All right, what is this K thing? So for the constant is A unitless. Now remember, in kinetics, the little k, the rate constant, wasn't unitless, but in equilibrium, the big K, the equilibrium constant, is unitless. If it is greater than 1, okay, that means products are favored. That is not how you spell favored. If K is less than 1, reactants are favored. And if K exactly equals 1, you're at perfect equilibrium. And the further away you go, the less equal it is. Okay? Less equal it is. Well, where can I find these values? Kc, Kp can be converted back and forth between each other, but there are a few that are in tables. But you have to match the condition for those tables. So always double check. Do I have the K value for this problem? And a lot of times the answer is yes. All right. You have the constant, and then 5, set up your ice tables. I know that was, woo, all of it together, but in a nutshell, that is what we learned from this chapter. All right, until next time, Jolly out.